All right, our next speaker is the virtual. So we will have Rayna Rampalli, who will tell us about from planetary formation effects to galactic influences, understanding our sun's unique-ish chemistry.
Hi, can everyone hear me?
Okay, Rayna, so since you are online, I guess I won't give you a warning, but if you are way over time, I will stop you. Yeah, so take
Oh,
care.
you can hear me fine though.
Yeah, can you speak louder? Try.
Yeah, can you hear me now?
Uh, no, sorry, give us a moment. Yeah. Just a moment. Just a moment. Yeah, I think the sound is now quite on yet. Yeah. Okay, Rita, could you please try to speak again?
Yeah, can you hear me now?
Yes, great.
Okay,
All right.
great.
Yeah.
Thanks everyone. So yeah, I'm sorry I couldn't be there in person. So thank you to the organizers for allowing me to present virtually. My name is Rayna Rampalli. I'm a finishing graduate student at Dartmouth College, and I'm going to be talking to you or continuing to talk to you about our sun and what's going on with it. So thanks to Kevin for really teeing this presentation up. I'm really excited to talk about this now. Before I get started, I just want to shout out all of the collaborators who've helped me put this work together. We have a range of astrophysical scales sort of represented in the expertise, which I think really allowed us to kind of build this narrative about the sun. So yeah, this was already covered earlier, but for the last decade and a half, we've observed that our sun seems to have somewhat of a unique abundance pattern compared to other sun-like stars, particularly when looked at in this sort of parameter space. So this is work from Megan Bedell, where she looks at a bunch of solar twins with really high res spectra, measures their abundances and compares them to the sun, and that's what we see on the y-axis. And this is plotted as a function of the element's condensation temperature. So the temperature at which 50% of your element is going to condense from a vapor to a solid. And so you can see as the condensation temperatures get higher and higher, the sun is looking relatively, more and more depleted in these elements, which we know as these refractory elements, which is of interest, of course, to the planetary folks, given that these really make up our rocky bodies. And so this is something we've observed, and we see it compared to about, at least a majority of other sun-like stars or solar twins. So the sun is definitely kind of in the minority here in terms of its chemical abundance pattern, which is somewhat surprising, right? Since we think our sun is fairly average in all senses of the word. So why are we sort of seeing this here? And so, yeah, we can think about this in terms of two different scales. So, Kevin touched on the kind of interior mechanisms here, which is, there's perhaps things going on within the solar system or within, the planets that are causing these refractory elements or refractory material essentially to be suppressed from the sun. Kevin has said that's probably not what's happening here. And spoiler alert, I'm going to agree with that. So that's great. And then on the other side of things, we can also think about this from the galactic side. Is this just a result of galactic chemical evolution that's driving this, refractory depletion? Is it a heterogeneity in the ISM? What have you. So these are the two areas I think about a lot and how these two areas sort of talk to each other. So our group sort of explored these scenarios, and we have an answer for you, I think. So we start with sort of the exoplanet or the planet side of things. And essentially, all we do is we take a population scale approach to this. So we take all of the exoplanet hosts that are sun-like in nature, that have abundances measured for them, and essentially do what you saw in a couple of slides ago that Megan Bedell did, which is look at how these abundances sort of compare to the sun's. And so we see here for our exoplanet host sample, the sun is still looking depleted in refractories compared to these exoplanet hosts. And so what that tells us is that planets are probably not the kind of biggest explanation here, because if that were the case, then we would expect other exoplanet hosts to sort of show the same refractory depletion as the sun, and we don't see that. And so what that means is that, planet sort of related explanations that sort of alter host star chemistries could still be at play, but they're not at play at such a scale that we can detect. And the fact that we can still detect the sun's refractory depletion compared to these other stars means that there's something else kind of at play that is causing this signature that we can see. And so that's really where we turn to sort of the galactic scale. And we just start by looking at just how these stars and their abundance patterns sort of behave as a function of these different stellar parameters that ultimately tap into galactic chemical evolution. So we go ahead and take all of the stars that are sun-like in nature, that have abundance information, and measure this sort of refractory depletion slopes for each of these stars. So we can collapse all of that information into one metric. And that's what we put on the y-axis. And then we go ahead and plot these, slopes as a function of these stars' mean metallicities and their alpha enrichment. And so when I say alpha enrichment, just as a quick reminder, this is looking basically at what kind of star forming environment these stars were born in, because it's looking at your alpha process elements, which come from your type 2 or core collapse supernovae that go off much more quickly than your type 1a supernovae that produce, your iron peak elements. So if a star is alpha enriched or enhanced, that means that, it was probably born during a significant bout of star formation. So that being said, if we go ahead and plot all of the data down and see how it looks compared to the sun, which is, normalized here at this slope of 0, we see some interesting things, right? We see that the most sun-like of the stars, so the stars with solar metallicity and solar alpha, are sitting somewhere down here. And so this means they're looking refractory enriched on average compared to the sun, which is what we've been seeing this entire time, right, for the last decade and a half. But then if we sort of look at where the stars that have the same kind of refractory slope as our sun sit, those really sit at this region where they're more metal rich than the sun, but also alpha depleted. And so because we're seeing this result, it sort of, hints at, galactic chemical evolution sort of being the explanation for driving these different kind of refractory slope trends. And so the question we ask is, okay, we're seeing some sense of it, but can we figure out sort of a more granular description of galactic chemical evolution that helps us, put this in a nice little bow so we can actually fully explain what's going on here? And so what we do is we take some methods from galactic archaeology, particularly those from Emily Griffith and David Weinberg that they've been working on. And what they do is essentially they are looking at how they can understand stars' chemical abundance patterns sort of more fundamentally from a galactic nucleosynthesis perspective. So we know elements are formed through nucleosynthesis, right? Generations of stars are forged from type 1a versus core collapse supernovae, combinations of the two. And so what Emily and David have done are sort of develop these data-driven methods of modeling stars' chemical compositions, essentially as a function of these different nucleosynthetic sources. And so that's what we do here. We take all of our stars and model them, model their chemical abundance patterns as a function of these two nucleosynthetic sources, including the sun, to see where the sun sits with respect to these other stars and their sort of nucleosynthetic diversity. So if we kind of recast these chemical abundances in this framework, we see the sun is very boring, right? It's sitting almost at the middle of the distribution of these sun-like stars and their element abundance patterns. This code sort of outputs these two amplitudes, ACC and A1A, that sort of correspond to the amount of enrichment coming from core collapse versus type 1a supernovae. And if we go ahead and actually take those parameters that are, empirically derived, and then calculate what, from those values, calculate what the expected slopes are for these stars, so a predicted slope from this data-driven model, we actually see there's like a almost perfectly one-to-one kind of match in terms of what the predicted slope is from these nucleosynthetic data-driven parameters versus what we actually observe with the spectroscopic data. And so with that, we can safely say the sun is not so unique. And the answer to why it's not so unique is really attributed to galactic chemical evolution. But the way we have to sort of account for galactic chemical evolution goes beyond using traditional stellar parameters, but using something more fundamental. So thinking about nucleosynthetic diversity of stars and where the sun fits in there. So with that, we'll conclude and take any questions. Thank you.
Yeah, very nice talk. Questions? Questions from the audience?
Hi, Rayna. This is Johanna Teskey from Carnegie Science. Nice talk. So looking at these plots that you have here, does this mean that for each star in the samples that you showed from each of those surveys, you have a ratio of the type 1a supernova enrichment to the core collapse supernova enrichment? Do you have that ratio for every star, or is it just on a survey by survey basis, if that makes sense?
Yeah, so I do have it for every star. I just, for the sake of some of these plots, just showed the mean distributions. But essentially, the way this is sort of, these numbers are sort of derived is sort of analogous to principal component analysis. So looking at, these chemical abundances and can we recast these chemical abundance patterns into one sort of prompt process versus one sort of delayed process. And how do those elements sort of fit in to those two categories? And then with that, we're able to get these amplitudes for how much enrichment is coming from each of these kinds of processes, which ultimately map to, these astrophysical nucleosynthetic sources, if that makes sense.
So quick follow-up, are you going to publish a catalog of, for each star, these ratios?
Yeah, so I have submitted the paper. It's on the archive right now, but once the paper is published, the catalog should be there.
Okay, we have time for one more question. Okay, go ahead.
Hi, Rayna. Nice talking. Hiki Jenny here from Gemini. So I just wanted to know what elements are you considering core collapse for the purposes of our study, and which ones are type 1a only?
Yeah, that's a great question. So the way this model works is actually very flexible. So, with typical, with alpha enrichment and that sort of thing, there's a very sort of prescriptive approximation that we use, right? That certain elements we're attributing entirely to core collapse supernovae, like magnesium, which is probably true, but, silicon and these other elements. But here, what this model does is it doesn't make that assumption. Rather, what it does is it sort of flexibly models for each element how much, what percentage of it is coming from core collapse supernovae versus type 1a supernovae. The only sort of assumption that's made to sort of calibrate all of these, the models, the KPM model from Emily, is that magnesium is 100% attributed to core collapse supernovae. And then I think 60% of iron, I'll have to double check, is attributed to type 1a supernovae. But those are the only two assumptions that sort of go into the model.
Thank you.
All right, great. Thank you, Rayna, again.
Cool. Thanks, everyone.
Thank you.